Yeah, myself, Kendaganda Swami, working as an assistant professor in the Department of Electronics and Instrumentation Engineering, RB College. Today we will discuss what is the general flow of digital logic design. We all know that any digital logic design starts with the problem definition, isn't it? So first we need to start with problem definition. Then from where we are getting the problem definition? So we all know that the problem definition we are going to be defining based on the customer requirement, isn't it? This is we are collecting from the customers, isn't it? And later, so we need to construct a truth table for that problem definition. Truth table. So once we construct the truth table, the next step is we need to make an Boolean equation. For that particular truth table, we need to write an Boolean equation. So we all know that there are two types of Boolean equations in any digital logic design. The first one is normal SOP or POS. SOP is nothing but a sum of product. POS is nothing but a product of sum. Similarly, the one more form is standard form. Standard form. It's also called as an canonical form. Canonical form. Again, in this also we have SOP and POS. See, this SOP is also called as a min term, and this is represented by the symbol summation. Similarly, the POS is represented in terms of max term. This is represented by pi. Now, once we write this, any one of the form, it may be a normal form or the standard form, so then we need to do the Boolean equation synthesis. See, why we need to do the Boolean equation synthesis? See, once I written the Boolean equation, for example, sometime the Boolean equation maybe comes in the form of, for example, y is equal to AB plus AB bar plus AB. This is the equation. See, for this equation, if I start designing the logic diagram, say it need one AND gate AB. See, then for AB bar I have A, and the B bar I will write one NOT gate. Then similarly, then I need once again AB. So then finally I am adding all the things with the help of an OR gate. So here the twice we are using AB in the equation. Why we need to use twice? So if I reduce any one of the term, obviously we know that we can possible to reduce the area, power and the timing, isn't it? Area, power and timing. This APT we can easily overcome with the help of Boolean equation reduction or synthesizing. So now what we need to do, the next step is we need to do Boolean equation synthesizing. Boolean equation synthesizing, or we can say reduction. In this Boolean equation, reduction and synthesizing, there are three types. The first one is there are three types of Boolean equation, four types of Boolean equation synthesizing or reduction. The first one is the Boolean algebra. And the second one is K-map, is also called as a Karnaugh map. And third one is QM method. This is called Quinn-McCluskey method. And the fourth one is WEM technique, variable entered map or map entered variable technique. So according to our syllabus, we are going to be discussing only these three reduction methods. One is the Boolean algebra, K-map and the Quinn-McCluskey method, but we are not focusing on WEM technique in our syllabus. The next one, once we get the synthesized form, see, as I said, with the help of this Boolean equation synthesis method, we can able to achieve power, area and timing. Okay, so we can possible to reduce these parameters with the help of Boolean equation synthesis. Okay, the next is, once we get the synthesized form, then we need to make an logic circuit design. Logic circuit design. Again, so once it comes to the logic circuit design, there are two types of logic circuit design. The one is combinational logic circuit design. Combinational logic circuit. And another one is sequential circuit design. So as I said, so which are all comes under the combination logic circuits. For example, if you take all the logic gates comes under the combination circuit, and if you take an adder, it comes under the combination logic. If you take an subtractor, comes under the combination logic. If I take an mux, it comes under the combination logic, or the demux, or if I say the decoder or encoder, this and all comes under the combination circuit. Similarly, if I talk about sequential circuit, in case of sequential circuit, all the flip-flops comes under the sequential circuits. Then the registers comes under the sequential circuits. Shift registers comes under the sequential circuits, or it may be an counter. So all are comes under the sequential circuit. So now we need to discuss what is the difference between this combination circuit and the sequential circuit. So now here I will enumerate all this, what is the combinational circuits and what is the sequential circuit. So before entering to this, the difference between the combination circuit and the sequential circuit, we should know what is the structure of combinational circuit and what is the structure of sequential. So if I want to design a full adder, see, this is the one full adder design. A 1-bit full adder. See, if I take a 1-bit full adder, see, this is the C in, and it is having an A and it is having an B. And similarly, we have sum out and the carry. And what is their internal structure? See, internal structure is, this is the one. It is having 2 XOR gates. I think you already know about this diagram in your first semester. Sum, this is the A, B and the C in, and this is the carry stage. These two are we are connecting to one OR gate. Finally, here we are getting the carry. Yeah, this is the one design is sitting inside the 1-bit full adder. See here, it contains only the logic gates. So that's why it is called a combinational circuit. So in this combinational circuit, for example, if I want to construct a 4-bit adder, so a 4-bit adder, so that point of time I need to replicate this one 4 times. Full adder, full adder, full adder. So totally there are 4 full adders. It performs 4-bit addition. So again here, this is the first position A0, B0, and this is the C in, and this is the first S0, and the first output of first full adder is connected to the next stage. This is called a cascading. So this is the C0 output. So then this become an A1, B1. Similarly, output of the carry is connected to the next stage. So this is S1, or we can say this is the ripple carry adder. This is also called a ripple carry adder, and the B2, A2, and again this carry get connected over here, and this is the C0, C1, and this is the C2, this is the S2, C2, and the C1, and finally we are getting C3 output here. This is for 4-bit with the help of an combination circuit. The same design, if I want to construct with the help of sequential circuit, this is the combinational circuit design of a 4-bit adder. The similar way, if I want to construct the same 4-bit adder with the help of sequential circuit design, so what I can do, so here I need only one full adder. I need only one full adder, and I need a one register, a 4-bit register. Here I am storing A0, A1, A2, A3. Similarly, I need one more register to store the one more B0, B1, B2, B3. So this will get connected over here, and here I am getting the sum output, and here I am getting the carry out, C out. So here I need a memory, to store the carry bit. So in order to perform the next bit information, next bit processing, so then I am connecting over here, this one I will connect back, and this becomes C out, and this become the C in of the next stage. So here it is having a memory, and here in order to operate this memory we need a clock. Memory, we can with the help of flip-flop we can possible to construct a memory, and here we have used register. Again register we can possible to make with the help of flip-flop. So it contains a combinational block, and it contains a sequential elements. So totally this is the 4-bit the 4-bit adder with the help of sequential design. This is the sequential design. I think now you are capable enough to distinguish between the combinational and sequential circuit. Now, the step by step we will discuss what is the difference between combinational circuit and the sequential circuit. So here I will clearly I will write what is the difference between this combinational and sequential circuit. So this side I will write the combinational circuit, and this side we will discuss what is the sequential circuit. Now we can easily find out what is the difference between the combinational circuit and the sequential circuit. So by saying this, we can say the present output depends on the present input, isn't it? So that is the first difference. Present output depends on the present input, but whereas in case of sequential circuit, present output depends on the present input as well as the previous output. Output depends on the present input and previous output, isn't it? So that's what I said. In case of combinational, the present output depends on only the present input. But whereas in case of sequential circuit, present output depends on the present input as well as the previous output. This is very, very important. The next difference is, see, in case of this combination circuit, there is no memory at all. Okay, but whereas in this case we need a memory. So that's why in case of combination circuit it doesn't have memory. But in case of sequential circuit it had a memory. The third point, see, as I said, if we not using any flip-flop, so obviously it doesn't require any clock. In case of combination circuit, it doesn't have any flip-flop element, so that's why we doesn't require a clock, so that's why it doesn't require clock pulse. Clock. But in case of a sequential circuit, we know that we are here we are using the registers and the memory element. Obviously we need a clock here. And the fourth difference is it doesn't have any feedback, but whereas in case of sequential circuit it is having a feedback. Okay, feedback not required. Here we need a feedback. Feedback required. And if you see that it requires which one requires more area and which one requires the less area, and which one operates faster and which one operates slower. See, whereas in case of combination circuit it requires more memory area. Okay, it requires more area. Combination circuit requires more area. More area to design. See, in this case this requires less area to design. And the sixth point, so in order to make this design is very easy, but whereas in order to design this sequential circuit it is quite difficult. So here in this case, simple in design we can say. Combination circuit is simple in design, but whereas the sequential circuit is complex in design. Sixth point. Now, once we come to the speed aspects, once we come to the performance aspects, which will be pretty faster as compared to this. Okay, so in the speed aspects, the combination circuit is much more slower compared to the sequential. This is faster compared to combination. This is the list of difference between the combinational circuit and the sequential circuit. So this is one complete the digital logic design flow. This is a complete overview. So in addition to that, in our syllabus we need to discuss the logic families. It comes the TTL, ECL and the CMOS. So once we come across all the things, in case of sequential circuit design, we are doing with the two models. One is Milli model and the Moore model. So in each and every chapter, we will discuss step by step each and every parameter what I discussed today in the introduction. So I will continue with another half an hour with the same introduction. So we need to know what is logic design, why we need to learn logic design. Is this the logic design, is the actual design, or the one which sits in the implementation, or is there some other interpret level in between the logic design to the actual implementation? Okay, and we should know the application where exactly after learning the digital logic design, where exactly we can possible to apply for actual practical aspect or the application.